Number 21. The gravitational self-potential energy of a solid ball of mass density ρ and radius r is e. What's the gravitational self-potential energy of a ball of mass density ρ and radius 2r? So let me illustrate this by drawing our sphere first with a perspective drawn. We have a radius r. But to illustrate in detail about the self-potential energy, we have the same volume, and then I'm gonna have infinite number of concentric spheres within it. And what am I gonna do with that? Well, eventually I'm gonna integrate it to sum them all up to find the accurate self-potential energy. Alright, so you get the idea how this works. So I'm just trying to illustrate or show you how there are like infinite number of sphere inside here. So each concentric sphere is going to take the dr, and I'm going to need two components to start. So mass of the shell, and also I need the mass of the interior. What happens is that in our gravitational potential energy, these two masses will interact or attract each other, and then when we have infinite number of this concentric sphere, we're gonna integrate and then find the total self-potential energy of this ball. So our mass of the shell is the area of the concentric shell. So concentric sphere will be the area of the concentric sphere will be 4 pi r squared times okay, that's area. Now I'm gonna multiply by our dr for each uniform concentric sphere. So I have a dr. So that gives me the area times the distance. That gives me the volume. But we're not interested in volume here. We are interested in the mass. So how do we convert the volume to mass? Well, you just have to use the ρ. So we have mass per volume, and multiply by the volume, you get the mass. And we are given the r here. So for now, I'm gonna make the r to be big so that we can integrate without confusion. And also, let me use a different color so that you don't get confused. Also, we need to find the mass of interior right before the shell. Well, it's going to take the volume of 4 pi, or actually 4 over 3 pi r cubed, that's the volume of the sphere, times the ρ. Okay, now we have the mass of the interior up to that r. Now I'm gonna use the energy, the gravitational self-potential energy, so it becomes du equals negative du equals negative g, the m shell, the mass of the shell, times the mass of the interior, and divided by our radius. Okay, this is very analogous to our gravitational potential energy we've seen in many courses. And I'm gonna plug them in before I integrate, and to see if I can pull out some constant. And negative g. Now I'm just gonna jam them up. And also you will notice that this du, or actually the u, when after you integrate, will be same as E, right? Because there's no kinetic energy involved or any other form of energy except this gravitational potential energy. So you will notice that we can combine some like terms here. For example, I see that rho can be combined and our radius can be combined and also divided by the denominator r, and maybe pi's can combine as well. So that's the like terms. So du equals negative 16 over 3 pi squared g, and r to the fifth. However, we have a r on the bottom, so we get the r to the fourth power, but that's gonna be, because we have dr here, so we're gonna really keep that r. So r to the fourth dr, and are we missing anything? Okay, it doesn't seem like it. Alright, so now I'm gonna integrate both sides. Okay, instead of integrating here, you do notice that since these are constant, I can just simply integrate at where the r to the fourth and dr are located. So when I evaluate this, I get u on the right side, and that eventually becomes e, because we stated as so here. And then we keep the constants as they are. Oh, we forgot the rho here, right? So you should have rho squared. And then this simply becomes r to the fifth over 5. And then, oh, it has to have 0 through r. Okay. So we simply evaluate this. Well, it's gonna have r here. Yeah. So ultimately we get negative 16 over 15 pi squared g rho squared r to the fifth power. So now let's go back to our question. It said our radius now is twice as large. If we have E equals these, so let's now plug 2r into where the r is. You have to make it 2 to the fifth power, but our r is still the same. So ultimately, we still retains all the constant in front of it, and the only difference from this original equation with our new equation involving with 2r within the r is 32 times E basically. Okay. Again, this is equal to E, what's in the purple here, and everything is going to be same except this 2 to the fifth. The r to the fifth still retains the same as in the purple. So eventually, when you create twice as large ball, well, our gravitational cell potential energy increases 32 times. So the answer is E.